Today we're going to talk about plate tectonics. All right, so this was an image that was originally a straight railroad track, and this is found in New Zealand. So I want you to think about what might have happened, thinking about forces that we talk about with movement of the earth. If you guessed earthquake, that would be the most logical explanation that would have caused these tracks to buckle the way they did. All right, so let's start with PANGAEA. In the late 1800s, Alfred Wegener claimed that the continents were once joined as a single landmass. That landmass was known as the supercontinent of PANGAEA. PANGAEA means all Earth. Over time, PANGAEA broke apart, and those continents that we know today drifted to where they currently are, their current location. This is the theory of continental drift. Okay? Now, there are several evidences that support the theory of continental drift and the idea of PANGAEA. The first one is mountains. The Appalachian mountain range found in North America lines up with the north part of Africa. That would be here. Okay, the second one is that the Mesosaurus, this animal right here, or reptile, was found in South America and in Africa. He was a swimming animal, and unlikely that he was able to swim because he was a freshwater swimming animal in between in a giant ocean made of salt water. The Glossopteris fern, which is the green indicator, was also found. It's a warm tropical plant found in Antarctica, as well as on all the other continents. And while they're not included over here, the Syngnathus was an on-land animal, and it was found on South America and Africa as well, and it was not able to swim. Therefore, how was it able to move from one continent to the other? While Wegener had all of these great theories and he had all of these fabulous pieces of evidence, he could not explain the most important part, and that was the why. Why were the continents moving? So therefore, he was unbelieved and not accepted with his theory of continental drift at the time. It later would become accepted, but that would be once he was already deceased. All right, real quick, let's look at how PANGAEA was changed from the supercontinent into the current day. About 245 million years ago, it was a supercontinent. About 200 million years ago, it switched into two continents. So it was Laurasia in the north and Gondwana in the south. Great way to remember that is Laurasia has Asia, and Asia is in the northern hemisphere today. About 150 million years ago, the rift between South America and Africa broke apart, and it opened, creating that part of the Atlantic Ocean. And then India separated, and Australia and Antarctica separated, became independent of each other. And then about 45 to 38 million years ago, roughly estimated at 50, the other continents slowly began to move to where they currently are today, including India merging up into the part of Asia, creating the Himalayan mountain range. All right, so there was some support that did come back and support Alfred Wegener's theory of continental drift and actually proved him to be correct. But this was again once he was deceased. They started to map the ocean floor, and they led to the discovery of what is known as the mid-ocean ridge, which is an underwater mountain chain. When they found this, they were able to answer why the continents were moving, which was the question that he had not been able to answer. So they found three big things. They found that age and magnetic properties were important, showing that the youngest rock was going to be closest to the new ridge and the oldest rock would be furthest away. They also discovered the idea and understanding of what seafloor spreading is, which is where the crust is being created. And the third thing was they understood and became aware of ocean trenches where the crust is being destroyed. So again, when you look at seafloor spreading, the youngest rock is slowly being formed from the magma rising up. This is when new crust is created. Every time the magma rises and comes out of the volcano on the ocean floor in the middle of that mid-ocean ridge, you basically get new floor. It pushes all the old rock away and causes that new ocean to be created right here. That new ocean is actually rock. It's on the surface of the ocean floor. This causes the continents to move in opposite directions. So as this picture indicates, they are moving. So the continents started moving away from each other. Okay? When that happened, you had this motion creating new floor, and the old continent that was already there is now being moved. So if something's getting bigger, that means our world is round, something else is getting smaller. That was when they realized and started studying underwater valleys and learning that the ocean floor was dense and there are parts of it that are subducting and sinking back into the mantle like right here. All right, so the theory of plate tectonics. The lithosphere is divided into the tectonic plates, and the continents are part of those plates, okay? So the continents go all the way into that lithospheric part, which is the base of the crust and the top of the upper mantle. The tectonic plates are moving on that lithospheric piece on top of the asthenosphere, which is that part that's allowing it to ooze and float. And they are moving at different rates of speed and in different directions. Because of that, we've come to develop the theory of plate tectonics. The oceanic plates are thin and dense, while the continental plates are thick but less dense. So again, all of it has an actual crust. If it's a crust, it's going to have an actual surface. The difference is the continental crust is much thicker than the oceanic crust because it does not have water on top of it. All right, so this is a picture. All the red lines are representations of the tectonic plate boundaries. As you notice, most of those boundaries outline the continents, or even named for the continents, with the exception of Europe and Asia being merged. Eurasia is on one giant plate, which is here, and that is because it's so large in size. We do have some breakups. You have this piece and this piece that are not on the Eurasian plate that are technically still part of Europe and Asia. And then you have this little bit of part over here in North America. But for the most part, the plates actually outline the continents themselves. All right, so there are 3 types of plate boundaries. Okay, 3. The first one is continental. And I'm sorry, the first one is convergent. There are 2 types of convergent that involve continents and 2 types that involve ocean. Therefore, one of them overlies, and there are 3 total convergent boundaries. So there are 3 types of boundaries and 3 convergent boundaries, okay? So at a convergent boundary, it comes together or it collides, all of which begin with C. Comes together, collides, convergent boundary. There are 3 types. The first one is going to be oceanic. It's when 2 different plates are going to come together and create subduction right here, where one plate goes underneath the other. And that's because this shape right here is being created, which is a trench. The second type of convergent boundary is continental oceanic. So you have your oceanic plate that gets subducted, forcing the hot magma to melt, and all of that magma then is forced up and it rises. When magma rises to the surface, we generally end up with a what? A volcano. So continental oceanic creates subduction, and it also creates volcanoes. Okay? The third one is continental, and there is no subduction, and there is no water, there's no anything. It's just 2 plates being forced to come together. Well, when 2 plates are forced to come together, they must go up in motion, and therefore you end with mountains. The second type of plate boundary is a divergent boundary, and that's where plates pull apart. They are moving away from each other. Magma rises between them and cools that new lithosphere, creating seafloor spreading. When seafloor spreading occurs, you're getting mid-ocean ridges and rift valleys. This right here is the act of seafloor spreading. The magma rises up, comes out. This is the new floor, and then the old is moved further away. This is all occurring where the plates are moving away. Your magma creates the rift valley in the midst. In the middle of all of this, which is the mid-ocean ridge, which is the underwater mountain chain. The third type of plate boundary is a transform boundary, and that's where plates slide past one another horizontally. They do not go up, down, or new. They do not create or destroy anything. They literally just move. This creates earthquakes, and the most common one that we discuss is the San Andreas Fault, which is found in California. This is the San Andreas Fault right here. And basically, this plate is the North American plate, and this plate is the Pacific plate, and they are moving in opposite directions. Okay? Now, what causes those plates to move? Well, we know we have the lithosphere on top, followed by the Earth's core in the middle, and convection's what's happening, the movement of material due to differences in density. We know that the mantle where convections occur, okay? Those convections are driving the hot, less dense part up and the cool, more dense parts down. We know that because the Earth's core is what's actually doing the heating. So it creates this circle. Hot's going to rise, cool's going to sink. And the circular currents carry the tectonic plates along the surface as they move. That heating and those plates are what is allowing the actual movement of the plates on the surface of the Earth.